So let's get started. On this particular problem, we have a beam. You can see it's this is going to be a pin connection here at B and a roller at A. And it has a dead load and a single live load. And what we want to find first is the maximum positive moment at C. And then the second part of the problem will be the maximum shear at C. So both those are going to require us to draw an influence line. So what I'm going to do first, we'll do part A first. So we're going to try to find the maximum moment at C. So remember, we talked last time that if I take my structure, which remember is a roller on the left side and a pin on the right side, and if I want to draw, say, the qualitative shape of my influence line, I can use the Mueller-Breslau principle. Now, if you remember, if I want to find the moment at C, what I do is I come at C and I actually remove the beam's ability to withstand moment. So I'll put a pin there. Okay? And then remember, I'm going to apply positive bending moment to both sections. So what we're going to do now is imagine how this structure will behave. So you have to ask yourself, this point, is it going to move up or is it going to move down? And I think under this motion, you'll see that it would move up. And then if I connect it to the points that I know are not going to move, then very quickly I have the shape of my influence line. So what I'll do now is I'll come down and I'll draw my influence line more properly. So this will be the moment at C. And remember, this will be as the unit load moves around some distance x. And then here's the end point. Here's C. And I now know that this is the shape of my influence line. So what is the value? Well, the critical value is going to be this maximum value right here. Now remember, that maximum value is what? That is the moment at C when the unit load is where? Well, at C. Well, let me go ahead and write in that this was 1 meter and this was 3 meters. So that means if I go back up to my problem, that value right there corresponds to my unit load being right at C. So all I have to find now is what's the moment at C due to that load. And that's not a hard problem to do. In fact, if I redraw it real quick, and I'll assume I have a reaction at A and a reaction at B acting up, and I've got this unit load that I'm trying to find. I'm sorry, there is my unit load. The dimensions here again are 1 meter and 3 meters. Now remember, I'm going to cut the structure right here, and I want to find the internal moment there. So you decide whether you want to use the left side or the right side. I don't really see any advantage. I'll just do the left side, just because. So that means that if I were to cut this, oops, wrong color. If I were to cut this structure at C, which means this piece is 1 meter long, I could then find the internal moment at C. And you'll notice my unit load is right at the cut, so it's not going to create any additional moment. So the only thing that's going to create moment here is going to be AY. So what is AY? Well, you've done plenty of these. If I sum moments about, say, B, and make sure I'm in equilibrium, I'll use right-hand rule for my sign convention, I can easily find AY. So summing moments about B, my unit load creates positive moment. Force is 1. The distance is 3 meters. And then my AY reaction creates what kind of moment? Negative. And that would be AY, and the moment arm is 4 meters. So it looks like AY is 3/4. Yeah.
The unit being right at the point and right next to the point is equal to the same thing?
Say that again. The unit load is what?
The homework, it says like find when the unit weight is right next to the point B, for example. Or in this case, if it said right next to point C and at point C, is that
That's the same.
the same? Okay.
So I now know my reaction here is, what was it? Oh, 3/4. So now I can find my moment at C. I just sum moments. This time at the cut that I just made. Make sure it's in equilibrium. In that case, with right-hand rule, my internal moment is positive. The moment created by the reaction is negative, and that will be 3/4, and it will be at a 1 meter distance. So my moment at C is what? 3/4. Actually, it has a weird unit of meters. So that means that over here, all these values will be meters, and this value here will be 3/4. So I now have my influence line. So now to solve this problem, how is the dead load and then how is a single concentrated live load affect this? So when we're looking at uniform loads, dead load, that's going to apply to the whole run. So if I do my uniform load first, what do I have? Well, I have a value of 500, and that's Newton per meter. And then what do I do with that? I multiply it times what? The area under the influence line. And my area is just a triangle. So the area of a triangle is 1/2 the base, which is 4 meters, times the height, which is 3/4 of a meter. Well, conveniently, my 4's cancel. I get 500 divided by 2, that's 250, times 3, that's 750. So that should be 750 Newton meters. And it's positive, so I get a positive value. So now my live load, there's my uniform load. So it's a concentrated load of 3 kilonewtons. So where should I put my 3 kilonewton load on my beam to create the maximum moment at C? Well, you use your influence line. And what's the maximum value? 3/4. And where is it? Right here above C. So that means that I will take my 3 kilonewtons and I will multiply it times 3/4 meters. And what does that give me? I don't know what that is. What's 9 divided by 4? 2.5? No, 2 1/4. And I'm going to change that to newtons to match this. So that'll be, well, I'll just leave it that way. 2.25, and that'll be kilonewton meters. So the total moment at C is, I just sum these two. So that's Newton meters, so that actually would be 0.75 kilonewton meters. So add those two together and you magically get 3. So there's the maximum moment at C created by this load combination. So in review, remember our dead load is applied over the whole structure. We can't control that. So that gives us this, contributes this value. And then now we can determine where the live load goes. And your influence line tells you that the largest moment at C is when the live load is right above C. and it'll be 3/4 of that value. So that's where we get this part. So now the maximum moment will be 3 kilonewton meters. And just to show you how that works, I'll redraw the beam. There's our original geometry. And I'll put the blue part, the dead load, that's going to go across the whole structure. And then the live part will be where? It'll be right here at C. So this would be my 3 kilonewton force. And I forgot to write here, this will be 1/2 a kilonewton meter, because it's 5 newton meters. So that's the load. That's the loading pattern that produces this maximum moment at C, right here. Okay? Any questions about that? So we're just going to do it again now for part B. I want to find the maximum positive shear at C. So hopefully this will work. I can just flip this up. My printer got a little spotty on me there. But you can still see there's my dead load, there's my live load. I'm trying to find the maximum positive shear at C. So I'm going to do the same thing we did before. If you remember, I'm going to redraw the beam. Again, we have a roller supported A and a pin at B. Now, if trying to find that shear at C, I'm going to put in that interesting looking shearless connector. Remember that? And then I'm going to apply positive shear to both segments. So looking at the left segment, this edge of the left segment with this positive shear on it, is it going to move up or down? Looks like it's going to go down, right? So that means this will look something like that. And the right segment, since it's fixed here at B, and I push up, this left edge will go up or down? Up. So I'll get some shape like that. So let's redraw it. Except this time we'll, again, be a little more formal. So this is now going to be the shear at C. And these are my points of interest. And it's going to look something like that. So there's the qualitative shape that I get from my Mueller-Breslau principle. Now remember also, I've got this extra advantage, is I know that this change in value here on the shear at C is equal to what? 1. So I know the change in shear is going to be equal to 1. I also know that these are similar triangles. They have the same slope. So this base is 1. This base is 3. So that means this height will be 3 times as big as this one. You see that? So that means really I have 1 piece here and 3 pieces there. So that means this is going to be what? 3/4, and this is going to be 1/4. So this should be 3/4, and this should be -1/4. See the change? It's still 1, and 1/4 is to 1 as 3/4 is to 3. Similar triangles. So you'll notice that when you do this on the exam, it just looks like the influence line is going to magically appear, right? Because there's really no work to record. If you wanted to, you could include this diagram to kind of show your thinking about how the Mueller-Breslau principle is working. At this point, you could write some equations if you'd like, but I think the most important thing is to always check, rise over run, 1/4 over 1, 3/4 over 3. They have to be equal. So now that I have this, what do I need to do? Just work the problem. So our dead uniform load, what is that? I'm going to go ahead and work everything in kilonewtons. So this is going to be 1/2 kilonewton per meter. That's the actual intensity. Now this one's a little bit different. You'll notice that this diagram, that there's a positive piece and there's a negative piece. Again, this uniform load is going to be applied across the whole portion. So I'm going to have a positive area and a negative area. I have to count for both of those. So I'm going to, and they're both triangles, so I'm going to factor out the 1/2, and then I'll just take them in turn. So starting on the left side, base times height will be 1 meter times a height of -1/4. Then the positive piece will be plus a base of 3 meters times a height of 3/4. So that's 9/4 minus 1/4 is 8/4. 8/4 is 2, right? The 2's cancel. It looks like you just get 1/2. And this meter is canceled by that meter, so you just get 1/2 a kilonewton. This is shear. Did I do that right? That makes sense? Right? That's 9/4 minus 1/4. That's 8/4. 8/4 is 2. 2 cancels 2. That's fine. Somebody check that. So then the live load. Now remember, the live load, all the live loads can move around. And it's 3 kilonewtons. So where should I put my 3 kilonewton force to create the maximum positive shear? Well, if I wanted to create negative shear, I'd put it somewhere in here, right? In fact, I'd put it right just to the left of C, where I'd get my maximum negative value. But for positive, I put it just to the right of C and get this positive value of 3/4. So the load is 3 kilonewtons, and the ordinate of the line is 3/4, which is what, 2 1/4? That's 9 divided by 2 1/4, right? So that means the maximum shear at C will be these two added together, which will be 2.75 kilonewtons. And if I redraw the beam again, let's see where this will do the... So I'll look at A again is a roller. I have a pin at B. So my dead load is again applied over the whole structure. Can't really do anything about that. Acting down, and that has an intensity of 1/2 kilonewton per meter. And then where do I put my concentrated load? Actually, it's just to the right of C, but you really can't visualize that too well, so I'll just put it there. And that would be 3 kilonewtons. So interesting enough, in this particular problem, if you flip back, we got the same basic position to find the maximum moment at C and the maximum shear at C. Is that always true? No. It just turned out this way. But probably. Pretty close. So any questions about that one?